Good afternoon, everyone. Welcome to today's webinar. I have Katrin Klingenberg, the PHIUS Executive Director, on the line today, and she'll be running this presentation. Real quick, if you look at your control panel, you do have the ability to ask some questions while we're going through the slides. We do have a large amount of attendees, so we'll only be able to take a few questions at the end. And with that, I'm going to hand it over to Katrin. Welcome.
All right. Thank you, Katrina, for the introduction. And I'd like to welcome everyone to our webinar today. And you can see here on the first slide the reason why we're all here and why there has been an overwhelming response to the topic that we put out is because passive building standards have emerged as a very viable option on our path to zero within the climate context. I think more and more cities that have climate action plans out, they are realizing that buildings are a key component to meeting these climate action plans, and they are starting to take steps and taking building energy efficiency very serious. So on the positive side, today we're in way better shape regarding that understanding of passive building principles and what passive houses and buildings are in the country, and that is a good thing. Only maybe 6 years ago, we were not anywhere close to as good of a shape that we're in today. So that all said, many of you online today are policymakers, and you know how difficult it is to push new standards forward and to put them in place. We have had a lot of inquiries from various policymakers who are becoming more familiar with passive building standards, and generally there seems to be quite a bit of confusion out there regarding two different building standards and certifications that are currently in our North American market active. And so with that, I'm realizing that I am not advancing. Here we go. To our topic today. So I'd like to talk today about the two different standards, the PHIUS Plus 2015 standard, as well as the Passive House Institute in Germany standard, and the lessons that we have learned along the way. And before I get into that in more detail, I think maybe a few words regarding the history of PHIUS are in order to let you know why we feel we are very well positioned to contribute to this conversation. In 2002, I built my own house. Some of you might be aware of that, in Urbana, Illinois, and I was the first one to use the Passive House planning package that the Passive House Institute in Germany had pioneered at the time, as well as the energy design targets and parameters that they put forward as a energy design guideline. And that house, my house, the Smith House, was also the first house that then was designed and built to these standards outside of Europe. Because of that work, we started talking with the Passive House Institute in Germany, and soon became independent organizations, but partners in promoting passive building standards outside of Europe and in the United States. So as we started implementing the European pioneered passive building standards and design parameters, we very quickly learned that the United States had quite a challenge, and not just the US, also Canada, North America in general, quite a variety of climate zones that posed new challenges. And I'd like to talk about these lessons learned as we pushed forward promoting and implementing passive buildings in the United States and Canada. All right, with that, just quickly again a recap of passive house and passive building kind of history and why we're doing what we're doing. Obviously, passive house and passive building standards, high performance building in general, is not a new thing. There has been an evolution in how we learn about passive building science, passive building principles, and how we have arrived at design parameters that can help us to very quickly dial in projects that meet our design goals. And our underlying kind of motivation here was back then in the 70s as a response to the oil embargo, as well as it is today, the concern about climate. At least for me personally, that has been my driving force since I started and co-founded PHIUS in 2003, initially as a housing development organization, and then later changed its focus to becoming a research and certification organization for all things passive building. So our climate is changing. We need swift action. I think we are all on the same page here. So to the evolution of the passive building standards that I would like to talk about today. This has been a long time in the making. This is not a new thing. And that is really good news because we have long-term experience with these technologies. There are projects around that have been in use for 20, 30, 40 years in the United States and in Canada. And the very first groundwork for this high performance, low cal, very low load building was laid in the early 70s in Champaign-Urbana, curiously enough, same place that I built my house in. And the initial work by the Small Homes Council at the time at the University of Illinois basically defined already all the core principles and passive building principles that we're using today. The next step, it migrated northward, and the Canadians took on the principles, super insulation, airtight construction, so on and so forth. And they were faced with quite a harsher climate. So already we're seeing a transfer of these principles into a different climate here with the Saskatchewan Conservation House by Harold Orr. And that project really brought it all together in a much more severe climate than the folks in Champaign-Urbana were working with. In the 1980s, actually, reports say that there were already about like 10,000 to 30,000. The documentation is not very precise, but that is about the range. People say that high performance building to a very similar level of passive house and building, what we think of it today, was underway. And there are reports that there was already something like a passive house movement underway with conferences all over the place. In Canada, people were offering free builders training, the government was, and actually some of the early pioneers are still active within our community, and we're very grateful to have them as longtime leaders in the field. For example, Joe Stieberich, who as a young man was the first director of the R2000 program, which at the time much more resembled a passive building standard than it does today. So just the gist of it, the design guidelines that people came up with in the 80s were already quite similar to the design guidelines that we're shooting for right now, like roughly a 15% design goal of the typical heating load of a common average home at the time. So the low load home tenant was already very much core to the design principles. In the late 80s, the interest in energy efficiency unfortunately waned, and the leadership that North America had taken in the high performance market took a back seat, and Europe took over, and most prominently the Passive House Institute in Darmstadt, and they were very aware of the work that had been done in the United States and Canada, and they essentially continued it and continued to develop it in 1996 and brought a significant addition to the concept, and that was basically a pass-fail standard, which we look at here in a second in more detail. And then in 2002, that is when I built my home, first project outside of Europe that applied these targets. And at that point, it was a an experiment, right? Can we transfer those principles and those design tools that worked very well in Europe and that had started to kind of migrate throughout different European countries? Can we also apply those outside of European more challenging climate zones? Then after 2002, right here in the kind of like timeline, you might see a little kind of fork in the road here and a little note that I have on the slide that says MINA-GP, etc. At that point, those of us who were working kind of like as kind of partners outside of Europe, we were in conversation with the PHI, of course, and various participants in that discussion, they decided that they had to adapt the standards based on their particular climate, based on their particular culture, conventions, so on and so forth. So the reason I'm mentioning here MINA-GP, that was, I believe, maybe one of the first ones that essentially took the same principles and energy targets, but really tailored them to their particular market. And if you go to the MINA-G website today, you will find that this is actually one of the most successful passive certification programs in the world, with about 3,500 projects certified, which is a very significant number. And then for Switzerland alone, other countries, the very cold Scandinavian countries, Norway and Finland, they also ran into issues with peak load, and they actually came up with some strategies that we later were able to benefit from. I'll talk about this a little bit more. As we had as we looked at strategies, how we could adapt the great design methodology of the design parameters of passive building to the varying North American climate zones. And that's exactly what we then did. We partnered with Building Science Corporation in 2015. Well, actually, before 2015, the new standards were published. In 2015, we did this research for new climate-specific passive building standards under a Department of Energy research grant, part of the Building America program, and it was published in 2015 by NREL, and this is where you can find this publication today. The image on the right-hand side that you can see right here, I'd like to mention that one. I think the other projects you all know, it's the Saskatchewan House, Harold Orr's, Dr. Feist's first Kranichstein House up on top, my house on the bottom right, and then all the way over on the furthest right, that was actually one of the first single-family homes that were certified in the United States under the new PHIUS Plus 2015 certification regimen. And very quickly, trying to bust a couple of myths here along the way, and again, stress that this development of high-performance building and passive house has been ongoing for a very long time, starting in the 70s as a response to the oil embargo. Understanding of dire climate consequences were already there, and people had motivation to tackle this. And here you can see, this is a document that I personally received from Robert S. Dumont, who unfortunately passed away a couple of years ago, one of the very first pioneers of this passive building research. And he sent me this proceedings introduction, where you can see on the bottom right here, they're talking about studies on the performance in windows and passive houses in Canadian conditions. So passive house and passive housing were terms that were frequently used during this first round of what one might call a passive house movement. And people very clearly differentiated it from passive solar. There was confusion. William Shircliffe, you can see right here, I have an image of his book, Super Insulated Houses and Air-to-Air Heat Exchangers. He was one of the very first researchers who really started to take to passive house, passive solar, and the differentiation. He started to collect and catalog all the different projects around North America and tried to define a typology that was emerging from super insulation to passive house to passive solar and all kind of like in between versions. But in general, he understood all of those along that scale from super insulation to passive solar as being basically at some point, he called them all passive houses, just one with more of a focus of passive solar, one more with a focus of super insulation. And in at the time, actually, in fact, at the end of 1986, I believe this book was republished again in 1986, he declared the passive house and building technology mature. And he basically said, like, this is the greatest thing. We're going to be good in the future. We have solved our energy problem. The only thing that we will now can look forward to is improvement in components and new vapor retarders that will be developed, better windows, and somebody might even invent a compact space conditioning system for passive projects. So, and that isn't actually what happened. And this is essentially where the Passive House Institute then kind of like picked up the ball and ran with it in Germany. Now, very quickly, just here to make clear that these initial passive building principles that we're talking about, the Passive House Institute is talking about 5 general principles. We've expanded them to a few more throughout all different climate zones. I'll talk about this in a second, but these basic principles of insulation, thermal bridge avoidance, airtight construction, ventilation system with heat recovery, and very good high-performing windows, those principles were all already codified in the 70s, and you can read up on them pretty much almost verbatim to what we talk about today in William Shercliffe's publications. The energy targets in 1970 to 1985, somewhere in there, were already, I mentioned this, very similar to what we're shooting for today. And the core tenet of these super insulated projects was essentially the same core tenet that we use today, and that is the idea of a very low load home, where the envelope does a lot of the work, and as a result, the mechanical system can be very much minimized. And at the time already, people were talking about very low loads, and you can see those right here. Basically, the equivalent to the 10 watts per square meter that then the PHI picked up on and ran with it. And here in the US, 1 watt per square foot. But the general kind of structure here of how to go about the design process: take care of the envelope first and set a target in terms of reduction, then take care of the loads, reduce them as much as you can to minimize the mechanical system, and then have airtight construction to provide durability and prevent any kind of like moisture failure. So I just noticed that this title right here, I forgot to change. This is specifically the diagram from the PHI that lives on the main website where they explain their standards that are in effect today, and where they explain the 5 principles that they are considering core of their design methodology today. Those 5 principles are, you might remember the half circle that I showed you earlier. That they are very straightforward. They are thermal principles. We have the same as I showed you earlier here: thermal bridge, airtightness, ventilation, windows, and insulation. But what you can see here already also is that in the previous slide that I showed you, here there's no special focus on shading and solar gain reduction. There's no special focus on enthalpy recovery. So we can already see a somewhat heating-dominated climate bias here in these simple 5 principles that are still on the PHI website today. And these thermal effects on the enclosure, we know very well. There are many published works about how to calculate them. The algorithms are well known. They are published, and they can be easily handled in a static and simplified modeling tool, like, for example, here the PHPP that PHI started to use in the 1990s to calculate the whole energy balance. Now, characteristics of passive house standards. There are similarities, of course, between the passive house standard from the PHI, the Minergie standard P, the version that the Northern Scandinavian countries created for themselves, and what we came up with here in response to the challenges in different climates. But generally, what we see in passive building standards is you have the space conditioning limit first. So in this particular case here of the PHI standard, you have a heating demand or load. There's an either or thing. You can qualify through either heating demand on an annual basis, or you can qualify through the 10 watts per square meter peak load. And in this particular standard, the assumption is that these targets work anywhere on the planet. And then what PHI brought to the table in the 90s and early 2000s here was the source energy criterion that was not yet spelled out during the early pioneer days. And that gives us essentially a design guiding parameter to calculate our CO2 equivalent emissions of the overall whole energy balance of the building, not just space conditioning. And that number we need to know because we want to know if we are meeting our global carbon reduction goals that we set forth in so many cities in our climate action plans. And then, of course, there's a qualitative criterion, the air tightness, that assures durability, prevents any kind of like humidity problems in the wall assemblies. And then that also speaks to some elements of quality assurance here that then on site will have to be proven that this is actually the case. And then also PHI over the years added a few additional certifications, the retrofit standard NFIT right here, that essentially allows the projects to have twice the budget of the basic passive project. And then over the last couple of years, they also added a few different levels here, the passive house original baseline, then one halfway to zero, and one premium that is zero or overproducing, speaking towards like we really need to tackle our zero energy challenge, and that is really what we are after with our standard setting. So essentially, in an overview here, now adding the numbers, what happened under the German protocol, you know the numbers, 15 kilowatt hours per square meter and year annual heating. And also, it was mirrored over to be used for cooling with an allowance for very humid climates where you need dehumidification. But the baseline for these demands are the same, 15 kilowatt hours per square meter and year. Or you can qualify through meeting the peak load of 10 watts per square meter, or 3.17 BTUs per hour square foot here. And then here now you see the number 38 kBTUs, or 120 kilowatt hours per square meter and year is our global carbon reduction goal that we need to meet and need to stay within with our buildings. And then the air tightness of 0.6 ACH 50. Now, when we first started trainings in 2008, we were very successful in our affordable housing community development organization, Ecolab at the time. And soon the Department of Energy found us and other folks found us, and our projects were published, and people wanted us to share what we had learned. We started the PHIUS professional certificate and training curriculum for CPHCs in 2008, and started training across the country. And a few of those first pioneers, most notably probably Mark Rosenbaum from the Northeast, showed up for our very first trainings and very quickly asked a very tough question. The question was like, why 15? Why is that valid in all climates? So this is where our kind of where we started to question and try to find answers to that question. Why 15? Why is that a valid design parameter everywhere? How do we know that that leads us to the best possible solution in any climate? So as we started to research where this number came from, we did ask the PHI the same question and didn't really get a very satisfactory answer. So the best that we have been able to kind of identify where this number came from is essentially, I believe, the 10 watts per square meter peak load tenet from the pioneers was actually taken, and then it was essentially the PHI folks designed a home, an end townhouse, most common typology in Germany at the time, home typology. They built a home that met this peak load, and that in that particular climate resulted in 15 kilowatt hours per square meter a year. In 2002, when I first built my house, the PHPP didn't have any provision for cooling in it. At that point, the entire methodology was still very much just focused on the heating aspect. And at that point, the folks at PHI started seeing more interest from outside of their climate region, and they began to think about, like, how can we answer that cooling question? And in one of the next iterations of the PHPP, actually, there was a cooling option. So the similar algorithms were transferred from heating to cooling, and the target was, and that is my understanding, simply mirrored over from the heating target. So that is how we arrived at the 15 kilowatt hours per square meter and year for cooling, I believe. So still, that would make that standard very climate specific for Central Europe. All right, so and arguably cost also plays a role in setting these standards. And in Germany, the PHI did their homework, and they did come up with a cost argument. And you can see those cost arguments graphed here, that if you improve your envelope from the right-hand side here to the left, you initially pay more money, your investment is higher, but also your energy cost is lower, so you're reducing your amount that you're paying on energy bills. And somehow, like in the cost structure of Central Europe and Germany at the point of 15 kilowatt hours per square meter a year, you can see this dramatic drop right there in the curve. And that was essentially the argument, that at that point you can get rid of the very expensive heating system, hydronic heating in Europe. And at that point, that saving invested in the envelope would then result, what you can see in the right-hand graph right here, in essentially the most cost-effective level of high performance compared to halfway measures along the way, like 30 kilowatt hours per square meter a year, or 20 kilowatt hours per square meter a year. And then the funny kind of curve that then jumps off the graph right here, as we go further over to zero, and as we're trying to add a photovoltaic system to zero out the remaining energy, at the time when this cost framework was set up, photovoltaic was so expensive that it was not cost effective at all. And that is basically reflected right here in these graphs. Once you hit this like magic point of 15 at the time in Germany, any investment in a photovoltaic system to become a zero energy building was just not cost effective. And that was actually essentially the argument that the Passive House Institute made in Europe, and was very successful within that framework. So as we now found ourselves in the United States, you can see right here, this is a map that was created by Global Buildings Performance Network, and they are headquartered in Paris. And they are working on high performance buildings across the globe, and they're doing a lot of research regarding these issues. They came up with this, what I found a very helpful map, and it opened my eyes when I first saw it. A map that actually graphs the level of heating degree days and cooling degree days, and also dehumidification demand, if you will. And if you look at Central Europe right here, and the climate zones in North America, we have quite a different variety and different challenges in the different combinations of heating and cooling and dehumidification. And so the first thing that then came to mind, and of course we had already experienced that during our design practice, if you're designing in climate zones where you don't have this very clear-cut, simple heating dominated condition with no dehumidification needs and no cooling needs, the passive measures that work like a charm in heating dominated climates or moderately heating dominated climates, they start working against you if you have a climate condition that is, let's say, 50-50 heating as well as cooling. So the more insulation you add to reduce your heating demand and your peak loads, the more on the other end you're increasing your cooling demand and the cooling peaks, because even if you keep all the solar radiation out, you still have internal gains in the building, and they just start working against you if you keep them in. So that brought up very quickly the thought that in a standard setting process, if you have those two conditions and the measures that you apply for heating, if they start working against you for cooling, that the standard setting process really needed to look at both in conjunction and not just like be like, okay, let's solve heating first, and oh, there's also cooling need, let's solve cooling separately and add it on like in a linear fashion. It is a more complex process that has to be employed to arrive at really good design parameters that take us to the best possible solution. So on that note, it might be worth mentioning that if you still stick with like a one-size-fits-all and not a calibrated heating versus cooling kind of standard system, if you just take one-size-fits-all, even if you add like the either or, like demand meeting or peak load, this can lead designers to make wrong decisions. It is a serious limitation on the design process, and if those targets are not set correctly, they can, for example, in one project in Canada that happened, very cold Edmonton climate, imagine the very cold climate of Edmonton, but at the same time lots of solar radiation. There was one project in Edmonton that essentially was able to make the European passive house standard, but only by maximizing the solar gains and the glazing area to the south. And arguably in a climate of that condition, very cold temperatures in the winter, a opaque wall assembly is a better choice than even if it is a triple pane or quadruple pane window, because that is always weaker than the wall assembly. And the larger the glazing area, the bigger the amplitude of temperatures in the building, because during the night you're losing a lot of heat and it gets cold, and during the day you might have too much solar gain, and so you get a very large temperature swing, and your comfort is challenged. It also creates overheating and potentially cooling loads that were not in existence in this climate before. Now, this is just one example, but practitioners who are designing in many different climates, they know that these are very sensitive dials, and the design parameters are constraints that will determine your outcome. So it's really important that these design parameters are correct. So here are a couple of slides from a 2011 study by PHI when they were starting to think about different climates, and they actually with this study confirmed what we said. We said like, well, the 15 is not true in all climates, and you can see all the scatter right here. They basically took the same end house, that the Kranichstein end house, and they drove that project through all different climate zones, and there's a yeah, well, arguably this is a lot of scatter here, and it confirms that 15 is not the right answer everywhere, for one. But then somehow they, I think they rationalized this by drawing this line through there, basically saying like, well, if we make every project in all climates meet 10 watts per square meter, then it's just the annual demand that floats. And that was exactly what we were seeing in the North American climates as well. The problem here is that I believe what the PHI, because of lack of experience really, did not realize is that 10 watts per square meter in year is almost impossible to meet for smaller structures in climates that have very big delta T's. So for my home, for example, I thought Urbana, Illinois was pretty similar to Germany. Well, absolutely not. It gets super cold in the winter and super hot in the summer. And to meet the 10 watts per square meter or 1 watt per square foot peak load requirement, I would have needed a 200 R roof, 160 in the walls, 20 R in the windows, and like, I don't know, like a 100 under the slab. And arguably that is no longer cost effective or reasonable, or it is just not possible. Building science does not support that claim that you can meet 10 watts per square meter in every climate. And not only that, so that is just like heating, right? So the more insulation you lay on, at that point also the cooling load is starting to increase. So trying to get anywhere close to this 10 watt per square meter peak load is really, really difficult to qualify a project for certification. And in practice, actually, over all these years that we've been certifying projects since 2009, we have only seen a handful out of the hundreds that are now in certification, because it is really difficult to qualify through this path. So what the PHI did not understand here, I believe, is that the correlation between peak design temperatures and heating degree days and cooling degree days is that correlation is really weak. And you cannot really generate a clear rule where it is a clear straight line. And this slide illustrates that here. So if we take Frankfurt and we look at the design temperature here for that, 14.5, and we are trying to find a similar climate in the United States. So let's say we go to Baltimore, but then when we go to Baltimore, if you move over to the heating degree days and the cooling degree days, obviously Frankfurt has quite a bit higher heating degree days and almost no cooling degree days. And now look at Baltimore, we have a serious cooling challenge in Baltimore. And you can play this throughout all different climate zones. There is no strong correlation. It is really quite erratic if you look at these relationships. So very quickly we get out of this very clear heating dominated condition, and it's very hard to find that in the United States anywhere. And if you go to Canada, you have the opposite challenge. And I thought I had another one here. We have another slide like this that is in our publication, Climate Specific Passive Building Standards by NREL published. It shows a similar condition with very cold conditions, that there are similar effects at work. It's very difficult to find the same kind of combination. All right, that takes us to PHIUS Plus 2015. And maybe I can go a little bit faster now, because this was all really like we need to understand where we're coming from, so that we can understand where we're going from here. So understanding that setting standards is a complex issue as soon as you accept that climate matters. It's a complex issue as soon as you accept that cost matters. And then there's another factor, actually, which I'll talk about briefly here in a second. Internal gains also matter. That's a different topic, though. But so all these different factors need to be considered to set standards that then will lead to the most cost-effective, comfortable, resilient outcome in terms of specifications for the envelope. So we switched away from the one-size-fits-all. We switched to, but you can see the general architecture is still the same. We're putting a limit on space conditioning first for heating and cooling demand. Now, heating and cooling demand are both different targets. They have been calibrated taking cost into account as well. And also the heating and cooling loads have been calibrated, and they also are now both different. And under PHIUS Plus, we're requiring all 4 of those having to be met, not just either or, because they all matter. They give you clues in regards to where your best envelope in terms of performance and comfort will lie. The source energy, we have that as well, and those numbers are pretty equal, consistent. PHI as well as PHIUS, we're referencing IPCC recommendations in terms of like how much contribution has to come from the building sector, calculation to identify how much per square foot we have to save in terms of carbon. So this is a non-negotiable target, right? We have to meet that to stabilize our climate. And then the third criterion here, quality assurance. And under our program, and this is might as well a different webinar because this is goes beyond of what we're discussing here. Air tightness ventilation testing, we decided to require the DOE, Energy Star, and Indoor Air Plus checklists. Quality assurance is very, very important, but that's again another topic, maybe another webinar by itself. Today we're just talking about the assumptions of our standards. They need to be correct before we even start talking about the differences in how we're actually doing these things. And then PHIUS also has 2 additional badges, PHIUS Plus Source Zero, because we're recognizing we have to go to absolute zero CO2 at some point. And we also have a supplier heating sufficient badge, which was a little bit of a notch to the functional definition of the PHI that says that a passive house is a structure that can be heated and cooled with by using the ventilation air alone, having heating and cooling integrated in the ventilation air. Again, another webinar by itself. We're just kind of focusing on the standards here today, and we're not going to talk about that supply a heating sufficient underlying building science. Maybe next time. All right, so as we looked at the principles, now back to those. You've seen the upper half here of this circle of the underlying passive building principles already. That is the simple thermal simple thermal effects that can be fairly easily calculated in a whole energy balance in a simplified manner, monthly climate data only, such as PHPP previously, and now under PHIUS Plus WFI Passive. You can see these upper 5 initial kind of principles that the PHI has up on their website got expanded by, so there are some critical climate-specific differences here. The second circle up on the shading and daylighting circle, very important. Shading and daylighting are crucially important as one gets into warmer climate zones and cooling demands and loads. And then also you might notice that one circle up from there, we say enthalpy, recovery ventilation. We almost always recommend ERVs for passive structures unless you have a reason that you really want to get rid of all the humidity in your building, like for example, a swimming pool. But generally speaking, we're recognizing that if you talk about ventilation air, you also talk about humidity management. All right, so then to the bottom half. And the bottom half here, this is where it really gets interesting. And this bottom half of the circle is no longer possible to reliably calculate in a static energy balance or static tool such as PHP or an Excel spreadsheet. To accurately assess the impact of moisture and thermal storage and interaction with the HVAC systems within the building, we need a dynamic hourly tool, and WFI Passive and Plus offer that to us and to our building science, to our PHIUS professional community. So we no longer just use a simplified static monthly climate data based whole building energy analysis, but we also have the capability to switch to a more granular assessment to the dynamic mode, which now can actually so imagine a climate that has heating and cooling and even diurnal swings, right? So it is no longer so simple. We have swings that go back and forth on a daily basis. The calculation is being affected by moisture and heat transfer through the envelope that goes back and forth, not as clear cut as like, okay, in the winter it always goes from inside to the outside, and in summer always from like outside to the inside. We now have more complex ways to assess the in-between times as well. And so you can see like the 5 basic principles that the PHI initially had has turned essentially in, let's call them 5 strategies here. These are the inner circles: the thermal control, air control, radiation control, dynamic performance control, moisture control. And each of those have 2 tactics that are being applied to put this in practice, and then of course with the goal to create a passive building that meets our overall carbon reduction goals, that is comfortable and healthy, is of high quality and durability, cost effective, so again affordable to the owner as well as to the society, and that is also resilient and can host 2 power outages. So again, we're talking climate here. It's not only trying to stabilize the climate, but we're already far enough down the road that we also have to concern ourselves with adaptation to the changes that are already in our way. And then here, a little video from the dynamic WFI Plus. I guess what I was trying to talk to you, describe to you here earlier, you can actually see in this little video, like the heat and moisture goes in both directions during various periods. And we can assess that in this more granular modeling tool. Now, cost optimization. So remember the slide that I showed you earlier, the German cost optimization argument that was created in, I believe, like, I don't know, maybe at the end of the 90s when PV was still really expensive. Well, it's out that our cost structure in the US is quite different. We don't have as expensive heating systems as hydronic heating. Forced air heating systems, gas are quite cheap. So the cost structure looks very different. There's no dramatic dip if we eliminate the heating system. If you really analyze the cost curve in the United States, it turns out that it is more like a shallow kind of like cup, if you will. And the choices are all equally good. Like some cost a little bit more, some cost a little bit less. But at some point, you definitely push back up into the diminishing returns. And we felt very strongly that the standards had to be economically viable, because otherwise nobody would be able to do it and nobody would be able to embark on this. So the new standards are dialed in as basically the sweet spot between conservation and generation, taking actual PV cost into account. And we used the NREL tool BOPT for that. We ran many thousands of calculations for many different climate files. This one here is the example from Chicago. And we actually were able to dial in where that bottom of that optimization curve is for Chicago. And we were able to also put it in relationship to the cost of PV as well as to the cost of solar thermal. So, and the results were surprising. So at some point, of course, PV at the cost right now becomes cheaper than upgrades into the envelope. And that is this little blip gray thing that you see all the way on the bottom there, close to the between the 60 and the 70. That's when the optimizer actually said like, well, hey, PV now becomes cost competitive with your envelope upgrades. And the funny yellow blip there, that is solar thermal. And in almost all cases, solar thermal was not cost effective. That was a surprise to us, but interesting result, of course. And then we also looked at where, if we had used the design guidelines that the European ones, 15 kilowatts per square meter in year for heating demand or 10 watts per square meter in a year, both of those targets would have pushed us significantly back up into the diminishing returns to a point where we were now even more expensive than the baseline. And you can also see here that both options are actually not equal. If you're meeting the 10 watts per square meter, you're even further pushed up into the diminishing returns in this climate, because it is almost impossible to do this for this particular climate. All right, so that took us to, and here for your comparison, the PHI targets on the right. This took us to PHIUS Plus in comparison. Now all the space conditioning targets for demands and loads vary by climate. They're all different. Air tightness, we switched from 0.6 ACH 50, which is based on volume, to square foot envelope area, because the thing with the 0.6 air changes at 50 is that that doesn't scale with building size. So if you're building a tall single family home, this is a fine value. But if you all of a sudden also assess projects that are 20 stories tall and have, I don't know, 200 units in them, the ACH 50 measurement, actually, it does not scale. If it meets 0.6 at that size, it means that it is actually quite a bit leakier than if you test a single family square foot home. So this was the reason why we switched to envelope area for the air tightness test. And then the source energy factor, we decided that it was a per person thing, fair share, essentially. On the PHI side, they still use for other countries 38 kBTUs or 120 kilowatt hours per square meter a year, and recently came up with a new primary energy renewable factor, which is a calculation that applies once your grid has been significantly decarbonized and your energy sources are coming from renewables. So it requires a more sophisticated calculation method. Once we get there in the United States, we will take a look at that as well, but we might be able to do this in a little bit more simpler fashion as well. Okay, so example right here, real quick. Check with time, totally running out of time, but that's okay. This is an ongoing discussion. So what I like to say here real quick, example for New York State, you can see that the climate specific standards are quite different. We have annual heating demand here in Watertown, coldest climate in New York State is at 7. Cooling demand is 1.6 under the new standards. The peaks are different as well. And then here for Albany, you can see we're going further south. The two are closer together. And then in New York City, they actually flip. The cooling demand becomes the deciding target for the designer to watch out for. And so the new standards actually make a very big difference in terms of cost, while it is true that if you designed a building in here, New York State for Zone 5 in New York City, if you designed the same building to meet PHI standards and the new PHIUS Plus standards, the envelope specifications will be different. The overall total energy performance in terms of site will be only slightly different. And it's true, PHI performs a little bit better, like maybe about 5%, but that really, given the energy costs right now, this is not a big deal. But what is a big deal is what the new standards were able to save in terms of percentage for all the different components of the envelope, specifically the slab R value and roof R value, and also the U value for the glass. And you can see this here for both climate zones, for Zone 5 and for New York City. The cost difference is significant. And all that just by giving up about 5% of site energy performance. And why does it matter? So here was a very fantastic, well, it worked out great for us, and I think it also worked out excellent for the developer, by the way. One of the very first large multifamily projects got underway quite early in Hillsboro, Oregon, and the Orchards at Orenco Phase 1 project, at that time, we were still working on the research and to finalize the PHIUS Plus 2015 standards. We knew what the issues were with the initial standards, but the project team wanted to go for passive, and they got an additional grant, and they went for it. So Orchards Phase 1 is actually still using the European one-size-fits-all targets. And you can see model performance and measured performance are somewhat in the same range right here. Well, while the model performance, this is not accurate. This is like after our assessments to fix what I'll talk about here in a second, what is off with the modeling protocol. But what is important to mention here is that it was 11% over typical project budget. And then at that point, the developer said like, nice try, it was great. We have an excellent building, but this is too expensive and we cannot afford to do this again for phase 2. And at that point, we had released PHIUS Plus 2015, and we offered them a free feasibility study. We said like, well, you value engineered your project, you're still going quite far. Please let us reevaluate your project. And turned out with just a few changes, they were basically right on the money with PHIUS Plus 2015. So that second phase then was quite a bit less costly, only 5% premium over typical. And again, they were still learning. That said, this is a very hot market, and the construction cost had increased significantly. So this 5% premium over typical, because these projects were apart by 5 years or so, 4 or 5 years, there's some just general increase in cost in the market in this 5% premium over typical as well. So that was a nice proof of concept for us. And ever since, we've never looked back. Most of our affordable, well, not all of our affordable projects now that use 2015 PHIUS Plus 2015 as their guiding design parameters, they consistently come in at about like 1 to 2% additional upcharge. The Charm project right here was still at 2.5. That was I believe that was maybe one of the very first pilots that we actually did. Okay, and that takes us to the internal gains. So so we've talked about climate sensitivity, how important that is that the standards reflect the balancing between heating and cooling. We talked about the cost parameter, that is really crucial so that people will actually continue to do this, and that it's doable for developers, homeowners, and such. And now there's another topic, and that is the internal gains, and they also are crucial to standard setting. When we were working on PHIUS Plus 2015, we did not embark on that one just yet. We were aware that it was making a difference, but 2015 also, similarly to the PHI standard, uses the most commonly inhabited structure in the United States, which is about a 2,000 square foot single family home. And we use that typology to dial in all the standards, basically with a reasoning that saying like small structure is worst case scenario from an energy efficiency perspective. And if you go bigger, it becomes easier. So surface to volume ratio gets better when the building gets bigger. So the assemblies actually get thinner. They become more cost effective. It becomes easier. So because we did not have tools yet to also take building typology and internal gains for bigger structures into account, we basically called it good, just like the PHI did with their end townhouse that they traveled through all different climate zones. But already in the early certification days, this is one of the very first projects here that got certified, and that is still under the old standard. You can see right here that what happened in reality, the PHPP prediction was actually significantly under predicting what then was actually measured. And then the right column is kind of pointless. This is in Oregon, mild climate, so it was relatively easy to meet the targets, and it didn't have to max out the total PHPP allowance here. So disregard the right-hand column. The important ones are the left one, what was modeled and predicted in PHPP, and then the middle one, which was actually what happened in reality. And you can see right here what I was talking about. Like the predicted heating wasn't even there because, with all the internal gains that were kept in by installation, nothing there, almost nothing, no heating needed in a mild climate. And then, but the blue, the miscellaneous all non-space heat, that actually included the mini split and the cooling demand, and the cooling demand was significant. So inadvertently, cooling demand had been created where there really shouldn't be any cooling demand. Now, we were looking at that and we're like, how can that be? Well, turned out that also the modeling protocol had an effect on what happened there, not only climate, but turned out that those guys had significantly more internal gains and internal loads than was actually assumed under the default standard calculation protocol in PHPP. And once we analyzed this, you can see right here, there's a gigantic difference between what best building practices in the United States, ResNet Building America protocol assume in terms of internal gains, lighting, and MELs here compared to PHPP. And so we knew that we had to adjust this. And in our new modeling protocol, we actually did. We switched away from those underestimating internal gain defaults from PHPP, and we're now basing all of our modeling protocols on 80% of ResNet lighting and 80% of MELs, ResNet MELs as well. And that made a big difference in terms of being able to actually matching modeled results with what actually happens in reality. Okay, so why is this important? This is all these different factors are now going into the design of projects. We have teams designing projects in New York City who are basically using PHIUS Plus 2015 and PHI based on like preference of their clients. And I was at a presentation at NESI not too long ago, and a very well recognized building science firm from New York City presented two projects which for all intents and purposes were essentially the same building. One was calculated under PHI standards and one under PHIUS Plus 2015 standards. 6-story, multifamily, same typologies, similar size, similar internal gains, different design parameters, climate-specific standards, one-size-fits-all standards, and different modeling protocols. PHIUS Plus updated, 80% ResNet internal gain assumptions, and PHI default internal gain assumptions. Now, the results of both projects showed something very significant. The PHI project was heating dominated and cooling was not an issue. The PHIUS Plus project was cooling dominated and heating was easy. So as an aware designer, essentially for all intents and purposes the same building, this should ring alarm bells. If a tool tells you two standards are being presented as like two flavors of the same thing, but one tells you you have to design to a crucial heating demand that you can't meet, and one tells you you're overheating, that both cannot be true. As designers, we have to be thinking critically, and this should have set off alarm bells with the design team, but apparently it didn't. They presented them both projects side by side, and they treated it as a numbers game. So at this point, I like to warn everyone, this is not a numbers game. If we don't have the right targets, we will create large-scale experiments that will overheat, and that will not help our agenda of making passive building best practices and code in the near future, because we cannot afford failing projects. And we do know how to do this correctly now. We have the tools, we have the computing capability. And actually, NYSERDA did a study, first third-party kind of comparison study between the two standards, PHIUS Plus 2015 and PHI. And the study shows some very worrisome results. Unfortunately, NYSERDA did not decide to tell people about those results. The worrisome sentence is buried somewhere in the middle of the report, saying like the unrealistically low internal gain assumptions in the PHI and PHBP modeling protocol are really worrisome, because if your internal loads are assumed to be too low, then that will lead the designer to draw the wrong conclusions, and it will affect everything down the road, like heating and cooling modeling results, as well as the choices of the mechanical system. So this has significant impact on the design and the accuracy of the design. We cannot just believe blindly the modeling tools. We need to validate the modeling tools and standards first before we can make this stuff code and incentivize it. So here's what we extracted from the study, and we were one of the main partners for that study. It was peer-reviewed. Everybody at PHI was contributing. We were contributing. We were calculating a 10-story multifamily building in New York City that was given to us by NYSERDA. PHIUS calculated the PHIUS Plus 2015 targets. You can see right here under the left-hand corner. Those are the results for PHIUS. PHI right next to it, exact same building. Exact same building, no, that's not entirely true. PHI criteria and PHIUS Plus 2015 criteria. The difference in envelope, the bigger the building gets, granted, the difference in terms of like additional insulation needed for the envelope is not as big as the 10-unit project that I showed you earlier, where the difference in investment was significant. Now, for this big building, you can see that PHIUS standards arrive at an R value in the wall at about 19. And the PHI standards arrive at a wall assembly of about 24. So roughly an inch and a half difference in terms of insulation, but the big difference is actually in the U value for the window. And you can see right here that that is a huge difference. The PHI solution actually still requires triple pane windows in that large type of a building, and that is a big difference right here. So it turns out that big buildings are internal load driven and dominated, and under our calculation, actually the relaxation of the envelope helps the cooling. It balances the cooling against the heating. But in the PHI protocol, again, like people are focused on the heating and not necessarily on the cooling. They're getting like some different clues right here. That's what these different parameters for the envelope design explain. But most importantly, what I want to point out to you here is the difference in modeling protocols. So we calculated our 10-story building. PHI calculated theirs. By our assessment, should be a difference of like 5% in site. But if you look at the site energy, the difference between the two is almost like a factor of 2. Like PHIUS says the site energy is 22, and the site energy under PHI says it's 13. Now, yeah, it's modeling. Do we know if this is going to happen in reality? No, at this point we don't. We don't have measured results. So let's assume that the reason for this extreme discrepancy, and same is true for source, is due to some different modeling protocol, which we have already identified. The internal heat gains are very different and very much underestimated in PHI. So now if we move over to the right column, you can see PHIUS modeled in eQuest and PHI modeled in eQuest. So basically what we tried to do here was like taking the modeling protocol out of it. So now we're just taking the specifications for the PHIUS project and the specifications for the PHI project, and then in the difference column, you can see now much closer, right? So we are probably on the right track here, that the modeling protocol and internal heat gains have something to do with a significant discrepancy if like the same project is being calculated in WFI Plus and PHBP. Now the next page is making this even now more clear. So Here in this one, we're now comparing the WFI passive model, PHIUS Plus 2015, to the PHIUS eQuest model. And you can see that the discrepancy here is much smaller. So we're within like 15 to 17%. We say we're better than eQuest. And I can, as a building scientist, I can rationalize that. I can say like, okay, WFI passive is more detailed. It's more tuned into high performance buildings. I can justify my model now. We've changed some algorithms. We have better granularity in our whole building energy analysis. Fine, I can live with that. That makes sense. But then now look at like PHI and PHPP compared to PHI modeled in eQuest, and you get like a huge discrepancy. So basically, PHI predicts almost like half of source energy that the eQuest model predicts, and site is similarly overpredicted. So significant. This is significant. Okay, now to what happens in reality. What we're seeing now in our projects is that actually the PHIUS Plus 2015 model is coming in quite close if we have good monitoring equipment in the buildings. So this is one of the orchards projects right here. And the monitored line right here, this is the green line, and the dashed kind of, what do you call this, like light orange line, that is the model PHIUS Plus 2015, what we predicted. So excellent matchup, really, in this particular case. And then modeled PHI standard and PHI internal gain assumptions shows about a 25% over prediction of what then actually happened in reality. And here you can see this again in these graphs, just bar charts. PHIUS Plus over predicted by about 2%, and PHI targets and modeling protocol came in. I think this one was roughly 25-ish, somewhere in there percent, and that's what we are seeing through most of the projects that we now get the monitor data from. This is a pattern. This is not just an outlier. And why does it matter? It matters to legislators because you have a mandate. You are spending tax money on incentives, on research studies to make sure that you achieve your goals in terms of carbon reduction and that you meet your climate action plan. Now, if you're using a tool and a program that over-predicts carbon performance by, as you saw right there, in like 1.5, 1.3 factor, that is a big difference. That is a significant difference, especially if we realize that our carbon goals right now, they are best case scenarios, right? We should be doing better than that kind of discrepancy of 30, 50% in the other direction. We should be overperforming and not underperforming. Same is true for the many Pennsylvania housing finance agencies, housing agencies across the country who are now incentivizing passive projects. They also want to know that the site performance is actually accurate and that they can base their cost effectiveness calculations and the projected savings, energy savings, on something that is real. So these numbers matter. Let's make sure that we have the best calibrated tools, best calibrated standards that match reality and measured results. And that almost takes me to the end. And I'm sorry I'm going over, but this is really important stuff. And I'm just going to finish this out. I understand that some of you might have to hop off. We will still be able to collect questions, and we will do our best to respond to most of them. We will kind of try to distill the most common ones and send out post a reply. So next steps, we are obviously in dire straits. Our built environment looks like this, like Jeannie Gang's Aqua Tower in Chicago. And again, it wasn't her fault. She had actually thermal breaks in her balconies that were value engineered out of it, but we have work to do. Our buildings are not safe for the global environment. So more lessons learned for the next steps. Basically, projects nationwide have really taken off under PHIUS Plus 2015. And we have high rises here, like the Bronx Tower in New York City, multi-family affordable projects across the country, all different climate zones. And the general site EUI here of passive is 10 to 25 kBTUs. For multifamily, it's like, let's say 20, 22, somewhere in there. The ranges happen because of building typology, size, smaller, better site EUIs than larger. And also climate makes a difference. So you can see right here the note, like 20 to 50% better than DOE zero energy ready home performance targets, and the 20% is, for example, for a project in Texas. In Texas, where there's cooling that dominates, the savings potential is not as great as in cold climates, and so that explains the range. And we have now 500 plus projects in North America throughout all different climate zones. And you can see that very slowly we're starting to see some activity here in the south of the United States as well, which obviously makes us very happy. It's probably worth also to note here that this is all different building typologies, not just housing. We have commercial, we have mixed use, schools, governments, all different building typologies are now possible under these climate-specific passive building standards. Side note, for complex, large commercial projects, we do generate custom design targets. Because of the internal loads, they are very different. Okay, so very quickly, certification trends in North America, and I'm the only reason that I'm quoting the Pembina report here that came out a couple years ago is because this is to date the only third-party policy market research study that has been published. So I'm not going to try to give you our numbers and ask you to take our word for it. They worked again with both with PHI in Germany and us and collected certification data. And this is essentially the distribution in the market. In 2016, PHIUS was certifying 95% of all square footage in the United States and in Canada. And you can see that since 2015, we have really been able to increase dramatically here, almost exponentially, while the PHI standard has kind of fallen a little bit flat. Now, side note, if you look at the other graphs, this is in units because we feel that units are most representative of how many people we put into a housing situation. But if you look at projects, the graph, it will show more like an 80 to 20% reduction. That said, a lot of PHIUS projects now are multifamily projects. I mentioned this earlier, or the slide said 80 plus projects. Most of PHI certified projects in the United States are still single family, and only 2 larger multifamily projects in Canada and in the United States. And then this is from 2016, 2017, PHI certified only 1 project in North America. So we certified 98% of all projects. And then aside from that, just PHIUS plus data, everything submitted to date looks absolutely stunning. That when we made this prediction in 2018, we're like, wow, this is really starting to look like an exponential hockey stick curve. And James Ortega from our certification staff just informed us yesterday during the staff meeting that during the first 4 months of 2018, we already certified and pre-certified as many projects as in all of 2017 combined. So given that, we already blew this projection here out of the water. A few more words of caution towards like PHI is often pegged as the international passive building standard or passive house standard. And there are amazing numbers that are being floated of how many certified projects exist worldwide. If you go to the Passive House Project of the database of the Passive House Institute, you see at first, if you don't really know how to use this, there are 4,294 buildings in the database, but those are not all certified. So most of those are actually self-reported, and some of our projects that didn't make it in certification, when we were still collaborating with the PHI, they actually self-reported themselves and showed up in here. And from our experience reviewing PHPPs, it was not uncommon that somebody totally thought they met the targets, and once we were done with the review, they were off by basically a factor of 2. So not anywhere close, or in some cases even a factor of 3, because they didn't know how to use the tool. If you really want to look and see how many certified quality assured passive house projects are there that were certified by the PHI, you need to click this little button there in the left corner up in the black box that says only certified buildings, that has a little PHI logo next to it, and then hit search. And then in the upper bar right there, you have the choice. You can choose a country, and you can actually like check out how many certified projects are in Canada and China, in America, and so on and so forth. So international applications. The United States is by far has the largest PHI certified projects outside of Europe. 10 of those are NFIT projects, which I mentioned earlier have basically twice the budget than the classic passive house project. So 48 are currently listed in the database. So let's say minus NFIT 38, and most of those are single family homes, and they are mostly located in the region that is very similar to the climate of central Germany. Canada has currently 16 projects listed on their website, and the country that leads PHI certified projects is Japan with 17. So if you compare that to the 500 plus projects that we now have on the ground in North America, that essentially represents a very good cross-section throughout most climate zones on the planet, I think you can make the case that we have very good climate-specific experience that is by all means globally applicable. And we have a new partner in Japan who's working with us on transferring climate-specific passive building standards as we speak to their cost structure and to their specific climates, which we're very excited about. And to conclude, very quickly, we're not done yet. Lots of lessons to be learned and still being learned. We just released the pilot program PHIUS Plus 2018. When we came out with 2015, we realized cost had to be dealt with, and that is a sticky wicket, of course, because it changes. And we essentially committed to a dynamic passive building standard at that point that would have to be reviewed and revised every 3 to 5 years, depending on what the market does. Now, the market has done quite a bit, at least in the PV sector. So we had to rerun and wanted to rerun, because we want to make sure these targets are as close to the cost optimum as possible. But we also incorporated a couple other really important lessons learned that I already kind of touched on here. But just very quickly overview right here, we have changes for heating and cooling. We're updating based on cost structure, and a few more lessons learned that I'm going to talk about here in a second. We are updating our approach to getting to zero. You'll see that. So we will now allow for photovoltaic and renewable generation to account at 100%. Before, we had only allowed production that happens on site. Now you can use all of it to zero out your source energy. But the heating and cooling targets still stand. You have to meet those first. And then, of course, quality assurance, we keep working on that one. As I mentioned earlier, quality assurance is a topic all by itself. We're now moving into commercial structures, quality assurance, looking at other related kind of quality assurance protocols, the American Air Barrier Association, and so on and so forth, kind of collaborating with other organizations on that one, as we have done in the past with the Department of Energy. But still the same, still passive building standards, so cooling and heating loads, peaks and annual, and we also still have the building energy performance standard with some prescriptive quality assurance requirements as part of this. Now, some of the critical things learned as we have moved into really big buildings with our certification. What really important lesson learned here is that bigger buildings have better surface to volume ratio. We knew that before. The envelope needs less upgrade, and than, for example, a single family project. And these two projects right here, right side by side in the climate of New York, Staten Island, rebuilt, very tiny single family home versus what is required for a large multifamily project. And again, those numbers right here, they are not dialed in yet. These were very early feasibility studies. You saw earlier in my slide that once we're done with the design and we specify everything and detail everything, the R value of the walls is more like in the range of an R20. So very important lessons learned. Small structure, worst case scenario, needs a lot of insulation, per square foot, obviously higher cost, much better windows. For a big building that is mostly internal load dominated, it actually helps to relax the envelope somewhat, and even the window quality, though not any further than where you get into the danger of having condensation on your window, and that is climate specific. And that is an additional requirement under the certification protocol. Another really important lesson learned, and that pertains to this window decision for a large building and a small building in the same climate. So one has triple pane, super high quality. One gets away with a very good double pane window. Components are climate specific. So are mechanical systems, ventilation systems, heat recovery, efficiency of the motor, enthalpy, humidity recovery, all these things matter. And then for components, of course, climate specific, where does the airtight layer go, so that we can have only one and not have like redundant layers on the inside and the outside. We can place it in the right place in the wall. It can be a vapor control layer, a vapor retarder, and give us a durable, well-performing wall assembly. And we have certifications for these climate-specific and typology-specific components now under PHIUS Plus. So recalculation. For 2018, we did take a slightly different approach. We did, and this is not necessarily where we set the standard right here, but basically we recalculated we recalculated projects, and I'll show you in a second how many we recalculated. We moved away from one single family home project for all, and we again picked the bottom of that optimization curve in the BOpt optimizer. And this is what we calculated here. We basically picked 5 building typologies. And to all architects, I apologize. These are not very pretty. BOpt is not pretty. This is really just to specify window to wall area ratio and some wall assembly specifications as starting point for the optimizer. So don't look at those as like the architecture of passive projects. This is really just for the sake of optimization. But we basically learned that not only climate matters, but also building typology and size matters, and also occupancy, i.e. internal gains, matter for the standard setting. I alluded to that earlier, and that's what we embarked on in 2018. So now we have the 2,000 square foot home still, the typical one, and we have a tiny home, that little guy right there, because so our kind of reasoning earlier went this way. The 2,000 square foot home, everything bigger is easier, but everything smaller than 2,000 square foot home was also harder and almost impossible to do. So we wanted to kind of essentially relieve that small homes penalty under the new standard. The new standard for now has been calculated for the 17 global climate zones under ASHRAE. So that works because that tracks with the heating degree days and cooling degree days. We still have to do more work to dial in the specific peaks. The peaks can the design temperatures can vary dramatically within these ASHRAE climate zones. So they are not as homogeneous. But for the time being, we're sticking with these 17 climate zones with more work to come to dial in the peak loads. So for 2018, as I said, we created a handy dandy calculator that lives on our website. And on top here, you can see ASHRAE climate zone, this drop-down menu. You can actually pick one out of those 17 worldwide global climate zones. then you can either use the slider right here to set your floor area ratio, or you can enter it in the box manually, and then you can set your occupancy again with the slider, or enter kind of enter it manually, and then the calculator spits out your space conditioning criteria here on the bottom. So for this larger project, you can see in climate zone 4A, let's say New York City, somewhere in that region there, that's what I said earlier. Like in that climate, heating for a larger building is not a problem. Your cooling demand is your main design issue that you have to deal with. And again, the peaks are fairly low because we're in a multifamily project. Peaks are tend to be very low in those. So just a couple more examples here. In this screenshot, the sliders are not activated. I just typed in this single family home here to show you this in climate zone 5B. And here you can see that this smallish home with an occupancy of 4 now again is dominated by the heating demand. It does have cooling demand, but definitely the heating demand here is the biggest challenge. And it is a small structure, so the total targets are a bit relaxed because that addresses the economic condition. And again here, same climate, just to drive this point home here, a floor area of 100,000, 200 people occupancy, so high internal heat gains. And you can see again the same thing here. It flips. The heating demand is not an issue, but the cooling demand becomes the one that you need to design to. Last 2 slides, promise, almost done. These are not the most pretty slides, and I borrowed them from Graham Wright. And he is the one who keeps us on the zero energy track and keeps us focused. And so, as he says right here, for the sake of everything, we humanity must get to absolute zero CO2 equivalent emissions. And this slide actually explains where this target comes from, this ominous like 120 kilowatt hours per square meter in year, or 38 kBTUs per square foot in year. This is a direct kind of result from the calculation of how much CO2 we can still afford to burn as humanity. The sad part here is, at least, and I hope that's still true, Graham, I will have to confer with you later, but I believe that these calculations in global carbon reductions are calculated to assure 66% of how to say this? We have a 66% chance to stabilize the climate if we meet these targets. And there's no budget for the unborn. So obviously, it is a very optimistic scenario and number that we're working with here. So the point I'm trying to make is basically an intro for the next slide. We must get onto the path of zero, and this is a point of departure for PHIUS Plus from 2018, from 2015. In 2015, we actually relaxed the per person target to 6,200 kilowatt hours per square meter year for residential a bit, because we realized our grid is really dirty and we needed some time to hone in our measures and to get to hope for components to become more ubiquitous, cheaper, more affordable, for manufacturers step up to the plate and come up with more efficient equipment. We always had the intention to tighten it back down to 4,200 kilowatt hours per square meter per person, which is equivalent to the 120 kilowatt hours per square meter a year that the Germans are using. For 2018, we decided to go even beyond that. So we're making good on our promise. We're tightening our source energy criterion now with a clear eye towards zero. You can see right here we're targeting 2050 to get to zero. My guess after the last discussion at the tech committee is that this will be aligned with the 2030 challenge, and you can see right here at the latest, we very likely will align with 2030 on that path to zero. So for 2018, these are your new targets per person: 3,840 kilowatt hours per person and 110 kilowatt hours per square meter, or 34.8 kBTUs per square foot. And that is on a glide path to zero. So in future editions, this will tighten even further. Now, to be able to do that, we are now allowing photovoltaics, renewable energy generation, to be counted at 100% against the source energy criterion, so it gives you basically an additional bullet to meet that target, but it will likely mean that a lot of projects will have to add renewable generation. And you can see right here, offsite generation, we accept that as well, but at a significantly discounted rate. That's a big step. It is reminding ourselves that the climate is real and that this is not just a numbers game. We have a clear target in front of us, and we have to achieve it. It is really crucial for survival of the planet. So last but not least, join us: Path to Zero, Comfort and Health, Chiron Action, Best Building, Passive Building Science experts in the field. Join us in Boston in September 19 to 23. Lots of workshops. We have microgrid workshops. We have mechanical systems workshops. Lots of new stuff that we see in the market that people are struggling with, we're going to address. We're very much looking forward to being in Boston, because Massachusetts as a state is moving significantly and putting a lot of resource towards the path to zero and zero energy buildings in particular. And last but not least, I like to reinforce the message that standards and certifications are not a numbers game. We need to make sure that our standards are the best they can be, and that our tools and calculation methods are the best they can be, and we need to validate. We need to make sure that our measured results match the modeled results, that our systems are good and ready to go to be successful, to make this ubiquitous and best building practice. And on that note, I like to end with climate tailored is the new green. And by climate tailored, we don't only mean climate, the outdoor climate, we mean it in a quadruple way, if you will. The local climate, the indoor climate, i.e. occupancy and building typology, the indoor climate in terms of health, and also the ecological climate, and of course, the global climate. So we need to be precise. We need to get to our goals, and I hope that you all will join us, and that we all can work together on this and continue an open scientific discussion about all these issues. We need every resource that we have, and we need to work together on this. And with that, I think completely blew through our time slot, but Katrina, do we have time for maybe one or two questions, or should we just
let's just do two questions real quick. I understand that a lot of you have to leave, so please feel free. We will record this last portion as well, so you can catch up when we send you a link. Kat, I first wanted to share a comment that somebody left. Kat, you're a rock star. Thank you, and I'm so happy to see big changes you've pushed in the sector since the early days of ACI in the late 2000s.
Thank you.
And then our first question, can you expand on the adaptation aspects of Passive House for the changes which are observed and expected in climate?
Well, I'm not sure I'm understanding the question correctly, Katrina. I believe that's what we just did by generating specific targets that guide the design of the envelope towards the cost-effective level of sweet spot between conservation and generation. I'm really not sure I'm understanding the question correctly.
I guess I understood it to mean how are we going to continue evolving our standards, and that's kind of what 2018 is doing. It's
yes. Okay, so that is actually that is a really interesting topic, and I would love to have another session on this actually, because as we're starting to develop partnerships, like for example with our Japanese friends, it's not only climate as in like local climate or indoor climate or global climate, it also becomes an issue of culture and materials that's available in that particular location, tools that are available in a particular location. And we definitely, I mean, there are regions in the world that have no computing capability. What are they going to do, right? Like we might have to develop even a kind of like a prescriptive shorthand for what we've learned, so that people who don't have those capacities in those regions can use them. And then also on our radar, of course, is the next step, the revamping of the grid, and how do passive buildings that now also incorporate some on-site generation, how do they interact with the grid? How can we help other organizations, like for example RMI, to develop exchange strategies, the internet? How can individual producers engage with that marketplace of renewable energy that is being sold communally? That is a really interesting question. And then of course also specifically technically, we want to get to the bottom of the direct current guidelines for our stakeholders, so that they can start to use those design instructions and start to incorporate direct current in their already super efficient passive projects.
Okay. Real quick before I ask the last question, I did want to point out that this webinar earns 1 CPHC CEU, but since we went over, we're going to up that to 1.5 CPHC CEUs. It's also worth 1 AIA HSW credit, so if you would pop your AIA number into the chat box, I will make sure to report those. And we'll just do this one last question. Kat, is there any measured data to correlate with the modeling comparisons that you showed on slide 27?
Without like flipping back to slide 27, I'm assuming that was the slide from the orchard at Orenco, and yes, for that project we have very detailed measure data from that project team, which obviously you kind of have to have, because otherwise you're guessing in many ways, and we have many more slides that break out all the different uses exactly. So I suppose the answer is yes, and there will be more presentations on that topic as we keep gathering data from various multifamily projects, specifically because that is really where the market is today.
Great, thank you. Thank you everyone who attended. We're so glad you stuck with us for the whole thing. Sorry for going a little bit over. We'll leave this open just a little bit longer so you can pop your numbers into the chat box if you need. But that's all from us. Thank you.